Good day, I am Dr. Ohlhoff and I will be leading this discussion on the solutions for Worksheet 12. So let's have a look at the first problem. We have to use polar coordinates to evaluate a given integral over a region in the second quadrant bounded by a circle and the curves x equals 0, which is the y-axis. The sketch shows the circle, which has its center where x is 0 and y is 1, and it has a radius of 1. We obviously are talking about the region in the second quadrant. That's why the left-hand side is shaded green, and that is the region D. We need to describe the region D in polar coordinates. The boundaries for theta are pretty clear. Remember, theta is measured from the positive side of the x-axis in a counterclockwise way. So we need to start at the y-axis, that is where theta is pi over 2, and we need to stop on the negative side of the x-axis where theta is equal to pi. For the boundaries of R, we substitute x equals r cos theta and y equals r sin theta into the equation of the circle. This gives us r squared cos squared theta plus r squared sin squared theta minus 2r sin theta plus 1 equals 1. Using the fact that cos squared theta plus sin squared theta is equal to 1, this equation simplifies to r squared equals 2r sin theta, and we can then cancel r, or more correctly, divide each side of the equality sign by r because r is not 0, and we find that r is 2 sin theta. It's also clear that r has to start at 0, that is right at the origin, so the smallest value for r is 0 and the greatest value is 2 sin theta. We are now ready to evaluate the double integral. The first thing we do is that we write the double integral as an iterated integral using the boundaries that we have just calculated. You can check the simplification. We end up with a double integral pi over 2 to pi 0 to 2 sin theta of r cubed cos theta sin theta dr d theta. Remember that you must make sure that the boundaries for the integrals match the actual variables. In this case, the boundaries 0 to 2 sin theta are for r, which is why the dr comes first at the end of this expression. Likewise, the boundaries pi over 2 to pi are for theta, and that is for the outer integral. That's why d theta is last of this expression. We now calculate the inner integral. The integral of r cubed with respect to r is r to the power 4 over 4, and we need to substitute the boundaries 0 and 2 sin theta and end up with the expression 4 times the integral pi over 2 to pi of cos theta sin theta to the power 5. We now calculate this final integral and substitute between the boundaries pi over 2 and pi, and as you can see, the answer is negative 2 over 3. That concludes our discussion of the first problem. Let's now have a look at problem number 2. In this problem, we must use a double integral to find the volume of a solid between two surfaces. The best starting point is always to make a sketch. As you can see in this case, we have two paraboloids, one that's concave upwards, that's the one with the equation z equals 2x squared plus 2y squared, and we have another paraboloid concave downwards, that's the one with the equation z equals 6 minus x squared minus y squared. And the volume of the solid that we must determine is between these two paraboloids. We need to determine the intersection of the two surfaces to find the shadow area in the xy plane that is below the body of which we must determine the volume. As you can see, the intersection is given by the equation x squared plus y squared equals 2, which is a circle with about the origin with a radius of root of 2. So we know that the solid lies above the circle with equation x squared plus y squared equals 2, and so the volume is given by the double integral over d of 6 minus x squared minus y squared in brackets minus 2x squared plus 2y squared dA, where d is the region enclosed by the circle x squared plus y squared equals 2. You must remember that the volume is always given as the double integral over d of the top surface minus the bottom surface. We are going to use polar coordinates to evaluate the integral. So for the region D, note that the boundaries for R is between 0 and root of 2, because the radius of that circle in the xy plane is root of 2, and theta goes from 0 to 2 pi. That is, it needs to make a full revolution. We can now write the double integral as an iterated integral and simplify. The integration is straightforward. You can check the calculations, and as you can see, we end up with an answer of 6 pi. That concludes our discussion of the second problem. In the third problem, we must find a suitable transformation to evaluate the given integral. Well, what would suitable mean in this case? The integrand is not very complicated. X times y shouldn't be too difficult to integrate. So the purpose of our transformation should be to find an easier region over which we need to calculate the integral. If you have a look at the proposed solution here, where we have x equals u over v and y equal to v, you can see that the product of x, y becomes just u. So if you look at the second pair of equations, xy equals 1 and xy equals 3, it means that's going to be reduced to u equals 1 and u equals 3, which is certainly much easier than xy equals 1 and xy equals 3. Remember that whenever you use a transformation, you have to calculate and incorporate the Jacobian into the new integral. In this case, the Jacobian is 1 divided by v. We now need to find the region S in the UV plane. That will be the region over which we will calculate the new integral. So let's see what happens. When y is x, it means v equals u over v, or u is v squared. That's something that's familiar to us. That's a parabola. Similarly, if y equals 3x, we get 3u equals v squared, which is another parabola. Let's have a look at the last two equations. xy equals 1 becomes u equals 1. xy equals 3 becomes u equals 3. And you can see what the new sketch looks like. Basically, the region S lies between two parabolas and two fixed values of u, namely u equals 1 and u equals 3. This is a very good example of a type 1 region. We can now convert the double integral over the region R to the double integral over our new region S. Remember that you have to add the absolute value of the Jacobian. The inner integral here is the integral of u divided by v with respect to v, which yields u times ln of v. You then have to substitute the boundaries. Note that the expression ln of root of 3u minus ln of root of u simplifies just to ln of root of 3. The integral of u with respect to u is just u squared over 2, and when you substitute the boundaries, the answer simply reduces to ln of 9. That concludes our discussion of problem number 3 and also of this worksheet. Goodbye and good luck.